Hi everyone, my name is Nelson Francisco. I'm a principal video compression engineer at MediaKind, and today I'll be presenting the paper Cloud-Based AI-Driven Super Resolution, which I co-authored with my colleague Julien Tanou. So over the past few years, the number of devices that support 4K or even higher resolutions have been increasing steadily or exponentially, if you want. With this trend set to continue for the next few years. Most TVs or new TVs are now at least 4K. Every device that is commonly used to consume media will have screens that exceed HD resolutions. But on the other hand, the availability of 4K or UHD content is still somehow lacking, especially on linear TV. So only a few events are in fact produced on 4K, with most of the content available actually coming from a video-on-demand providers such as Netflix, Amazon, or Disney+. So, having some kind of technology that can help to accelerate this widespread availability adoption can be a way of making this content more widely available. And we believe that super resolution can be a way of achieving that by allowing people to leverage on their current production pipelines, including their cameras and every other element in the production pipeline, and then just have a high quality upscale before distribution. So yeah, when you're consuming a video on your 4K screen currently, if it's, most content is, as I said, 1080i, 1080p, 720p, or even lower resolutions, it will, on most cases, be deinterlaced and upscaled at the device, and that comes with a few issues. First, your upscale will depend on the device capabilities, which is a problem on itself, because as you will imagine, if you have a high-end TV, the upscale is likely to be much better than if you have a budget offering. And also, if you're talking about mobile devices, power consumption is obviously an issue. So the upscale is usually quite constrained. By doing a high-quality upscale before distribution, you can throw much more resources at the problem and also make it much more green or efficient, since you only do it once. And every single compatible device with 4K, that's able to decode 4K and display 4K will be achieving the same quality and not depending on its upscale capabilities. The first approach is still good for some applications like peer-to-peer video or like video conferencing, or also old legacy content that isn't accessed very much. So that's why NVIDIA and Microsoft are offering their in-browser or in-play AI upscales. But those also have some issues, since they have to achieve the upscale real-time during playback, so they are quite constrained. And they usually require you to have quite a high-end consumer-grade GPU. So that's extra power as well. Not everyone can benefit from it, and the quality is, well, to anyone's judgment. The drawback of doing the upscale at the distribution side is that, obviously, if you're distributing video at higher resolution with higher quality, you will likely require higher bitrate. But because this also may allow you some room for content monetization, because in fact you'll be supplying your viewers with higher quality content that may be justified. So as I mentioned in this presentation, we are approaching the use of deep learning to do that video super resolution. So video super resolution, as most of you will know, is basically the process of getting a video or image and increasing its resolution. So there's, it's been out there for many, many years with the first methods relying on simple upscale, such as bicubic or Lanczos filtering. And then, it evolved to some more sophisticated methods, such as prediction, statistical, patch-based or age-based methods. And right now, it had a new breadth of interests driven by the deep learning progress and innovations in this area. So there's many classes of algorithms, each one's with their strengths and weaknesses, let's say. But also for practical implementations, it becomes very easy to find the sweet spot between the computational complexity and the results, because you tend to have diminishing returns. So our solution is based on generative adversarial networks, since we believe, and I'll try to justify that later, that it provides a very good balance between picture quality and the cost, or in the case, computation. It uses multiple frames and fields to do the upscale, so that it has a temporal component, and by using multiple frames of fields, that allows us to do the interlacing and upscale at the same time, since there is vast amounts of legacy 1080i content and archive. We architected it to run in the cloud, since that allows very scalable deployment. We are cloud vendor agnostic, although we're partnering with Microsoft. As I said, it's offered as a transcoding service. So you just upscale your content, it's processed in machines that are GPU accelerated, it's re-encoded, and you can retrieve it from a safe storage bucket. Again, we choose the cloud just because of the vast amount of GPU power that you have there, and you can scale it up and down depending on how fast you want to achieve your upscale. So far, we're not achieving live yet, just not because we can't, but because we are still working on the most efficient architecture to do it. But by parallelizing it, you can run it in multiple GPUs and achieve potentially live. That will open to other applications, such as live sports, where in a stadium you're likely to have 1080i cameras or 1080p cameras, and you may want to use them to complement your 4K transmission. So, as I said, right now you're probably questioning why using GANs and not other, more trendy AI approaches. Right now everything is about transformers and diffusion and all those new trends. So in order to try to justify why we believe the GANs are a very good balance between quality and computational complexity, we selected a mode, an algorithm that is technically considered to be kind of the state-of-the-art on that area. This comparison here will be performed for single image super resolution, so we're kind of trying to abstract from the temporal component to make just the comparison easier and just focus on the spatial equity of the methods itself. But you will have equivalent methods to deal with video super resolution for each of these classes of algorithms. So the RRDB is a PSNR-based model. ESR-GAN is kind of the state-of-the-art in GAN in the literature. Then SRFlow is a flow-based method. Then we have Swim2R, which is a transformer model, and SRDiff, which is a diffusion model, since SR3 from Google is not available open source. So you also have the references for each method if you're interested. So we run that, as I said, as a single image on the Diff2K validation dataset using a 4 times upscale on each direction, which is probably much more that you'll use in a video application, where you probably will be looking at a 2 to 3 factor, but that's really to emphasize the difference between the algorithms. And we are computing the PSNR, SSIM, the LR PSNR, which is basically the PSNR between the low resolution input and the super resolution image downscaled back to the original resolution. And we found that to be very good to show the correlation between two, to see if there is no network hallucination or any issue like that. And we also including the LPIPS, which is a deep learning based metric, which is very good at capturing the amount of detail, so it's present in an image. So that's why it's very commonly used in the literature in this area. So I'll also give an idea of the number of parameters of in the network, so you can kind of compare the ballpark complexity of each one. And also, I mean, for the GANs method, because it's an adversarial method where you have 2 networks, there is the second term is the number of parameters in discriminator that is only used for training purposes, so it becomes irrelevant when you're in fact running it to do your upscale. So just to show a bit of some details, not sure how good those can be seen in the screen, but yeah, focusing in a small window, you can see that those results agree a lot with what we could see in the HELPIPs. So the bicubic, very soft, and so is the RRDB, and so is the transformer method. Also, sorry, just going back, the LPIPs is a metric which is the lower the better. And by looking at these metrics, you can see that RRDB improves, which is the first deep learning method, improves over bicubic on every single metric. Then the transformer model is another step up, and then it becomes a bit more mixed. So ASRGAN has the best LPIPs, suggesting sharper images, but you can see a quite low LRPSNR that suggested, well, maybe the image is not so correlated, so that detail can be a bit fake sometimes. And then the other methods are much closer together. On the bottom, we have our own proposal that, as I say, uses a GAN, but it has several optimizations, namely on the optimization loss, which is an hybrid loss, as I said, which is an adversarial network, and simple loss. And also, we changed the structure of the residual net. So we have pretty much 10% of the numbers of weights of the other methods while we achieve pretty competitive metrics. So as I said, bicubic, RRDB, and SWIN2R agree with the LPIPs. They look quite a bit softer. ESRGAN, that had the best LPIPs, you can see it's actually sharper than the other ones, but then some of that detail may look a little bit artificial. And then if you look at the three bottom methods that are respectively the flow-based method, the diffusion method, and our method are quite comparable, even if they have quite different computational complexities. And then if you focus in that on the computational complexity, you can see that by having much less weight, we are much more lightweight and we can run much quicker. Just to have an idea, if we focus in a GPU with a similar-ish performance that what we used for this inference, you will see it costs around $3 per hour. Of course, this will depend on how much are you scaling it, and if you are using spots or something like that will allow you to decrease costs. But this shows you how the cost and difference time scales very quickly. And you see like the diffusion model, because it's iterative and it requires like 100 passes to refine your image, takes 30 seconds per image. If you're trying to process 60 frames per second, that becomes an issue very quickly. So, if you're treating a single or upscaling a single image, waiting 30 seconds is not a problem. Or if you're using a diffusion model to create you a cat astronaut big image, you're probably okay waiting a few minutes for it to do that. But when you're trying to upscale those many frames and big frames, it becomes an issue very quickly. So this is an example now for the video super resolution. So now it uses the temporal component and it's doing both the interlacing and an upscaling, and again focusing in the detail, where in the left you have typical YADIF, the interlacer, followed by a bicubic upscale. On the right, you have our method used to do both. Again, not sure how well you can see it, but we have a demo in our stand that you are more than welcome to pop and have a look and make your own mind. So another detail, well, you can see similar trends, quite much sharper, lots of detail is recovered that was not in the source, overall much closer to a real UHD experience. So to summarize, so we are offering this as a cloud solution, so very easy to test it, very no big investment. It's been trained over a wide range of content, also included pre-compressed content to be able to deal with all kinds of issues prior to the on your processing pipeline. Obviously, realistically, you not expect to have very bad quality content and this to upscale it UHD pristine. Of course, your results will always depend on your source. Also, proudly, we were just awarded with a Best in Show award in NAB for this solution. So I guess that's it.
Okay, thank you.